When we left off in our last video, we had begun to our discussion of Dalton's indivisible solid sphere model. And this is the model, really one of the only models that came out of what we would consider to be studies in chemistry, specifically chemical reactions. We had mentioned that the law of conservation of matter was discussed by Lavoisier. Whatever goes into a reaction, whatever matter goes into the reaction must come out. We talked about the law of definite proportions, which just says a given compound is always made up of the same recipe. In other words, you need the same masses of elements, same ratios of masses of elements to make that compound. The law of multiple proportions, that's the one that says different compounds different compounds made up of the same elements have to have a different recipe for those elements. Well, those three laws can best be explained by atoms. And this is where Dalton came up with his atomic model. His model is often called the indivisible solid sphere. Slang, it's kind of like called the billiard ball model or the BB model. We already know that there was problems with Dalton's model. There were no subatomic particles in Dalton's model. Dalton's model also said that all atoms of the same element are identical. They're not. Atoms of the same element only have to have the same number of protons to be considered the same element. Well, we know of isotopes. Different elements can have different numbers of neutrons in the nucleus. Atoms of the same element can have different numbers of neutrons in the nucleus, giving them a different mass. What did Dalton say? A very famous theory came out in the early part of the 19th century. All matter made up of indivisible and indestructible atoms. Well, we know that atoms actually can be destroyed in nuclear reactions. We know that the matter in an atom can be converted to energy in nuclear reactions. So that part is mostly true. And atoms can be divided in nuclear reactions, not in chemical reactions. Atoms of a given element are identical. Well, we already mentioned that there are isotopes present. They're not identical. They do have the same number of protons, but Dalton knew nothing about protons, neutrons, and electrons. Atoms of different elements have different weights. That is true. And atoms of different elements have different chemical properties. That is true. Atoms of different elements combine in simple whole number ratios to form compounds. That is true still to this day. And that helps explain the law of conservation the law of multiple proportions and the law of definite proportions, Proust's law. Atoms cannot be created or destroyed in a chemical reaction, and that is true. And that explains the law of conservation of mass. When a compound decomposes, the atoms are recovered unchanged. Decomposes means a compound is broken apart into its elements. That is true, and they'll always come out in the same ratios by mass. So that was Dalton's model, and again, there are some problems with the model, and that's why there are 4 other versions of it that followed this one. But Dalton's model really lasted, his idea of the atom lasted for really about 100 years. His came out around 1803. Around 1897, J.J. Thompson, also an Englishman, made an important discovery. He discovered the first subatomic particle, which led to a new model of an atom coming out. Now, the discovery of this first subatomic particle, which we now call the electron, surprisingly came from studies in electricity. Thomson did experiments with what we call a cathode ray tube, and it led to the discovery of the first subatomic particle. A cathode ray tube is a tube that's filled with almost nothing. It's a vacuum tube. There's very, very trace amounts of gas in there. And what scientists found out was you could conduct an electric current through this tube. And what they did was put a piece of fluorescent paper inside that tube, And when this electricity went through this tube, it caused that a glow on the fluorescent paper, because fluorescent paper glows when energy hits it. So they could actually see the ray, and they called it the cathode ray. They called that ray going through the tube the cathode ray because it started on the negative terminal, which is called the cathode, and it moved towards the positive terminal in the circuit, which we call the anode. So it was called the cathode because of where it came from. If you notice, the terms cation and anion also relate to the terms cathode and anode. The cathode is the negative terminal. The anode is the positive terminal. The cation, we know, has the T in the middle. It's the positive ion. Cats have paws. Why did they call the positive ion a cation? Because positive ions moved toward the cathode. Anions are negative. The big N in the middle of the word anion, negative. Why did they call the negative ion an anion? Because it is negative and it was attracted to the positive electrode, which we called the anode. So what happened to this cathode ray? Thomson began to study the cathode ray. He did it by putting a positive and negative plate outside the cathode ray tube. And that ray bent towards the positive plate, which meant that that cathode ray had a charge and it was negative. What else did he do? Well, he varied the metals that were used for the cathode and anode. Some say he even changed what trace gases were inside the tube, and he found out that the ray behaved the same every time. So he knew that this cathode ray was really common to all matter. This cathode ray had nothing to do with being part of a particular type of matter. Then he shot that cathode ray at a paddle wheel placed inside the cathode ray tube. So he took a small wheel and put it in there, and when the cathode ray hit that wheel, it caused the wheel to turn. And that let Thomson realize that whatever was traveling through that tube, that negative stuff going through that tube, had to be matter. And then he actually varied the strength of the charges of the plate to get an idea of about how big or how massive that particles were that were in that ray. And he found out that the particles in that ray were ridiculously small. So whatever this ray was smaller than the atom. It didn't matter what matter made the ray, so it was common to all atoms. So he was able to conclude that that ray had to be common to all matter. In other words, all matter had to have a negatively charged particle, which he called an electron. Or he didn't call it an electron, but it was called an electron. So what did they do? Thomson had to revise his model. He put the electrons, this negative particle, right inside the solid sphere. And he realized if there were negative particles inside the sphere itself had to have positive particles, or the sphere itself was positive. This model, Thompson's model, became known as the Plum pudding model. Why? Well, Thompson was an Englishman, and a dessert in England at that time was called plum pudding. It was essentially pudding, which was like a dough-like material that had plums embedded in it, the same way that electrons, Thomson believed, were embedded in the atom itself. In the United States, if this was discovered in the United States, it might have been called the blueberry muffin model, because it's a little bit more like blueberry muffins the way we look at it. The muffin would be the positive part, the blueberries would be the negative particles embedded in it. Obviously, there was a problem with this model. We know many problems, but at the time they knew there was a problem with the model, because if the electrons were negative, where was the positive part of the atom? So the search began for the scientists to begin to explore the rest of the inside of the atom. That exploration was made very easy, and Rutherford's the scientist credited with interpreting the experimental results. Remember, they wanted to start probing the inside of the atom to try to find this positive part of it. So how do you probe an atom? How can you tell what's inside an atom? By shooting something at it. Right at this time, at the latter part of the 19th century and in the early part of the 20th century, in the late 1890s and into the early 1900s, scientists were discovering what is now called radioactivity. Radioactivity is the process where atoms spontaneously change into other atoms by having pieces of the nucleus break off for unstable nuclei. So particles were breaking off the atom. One of the particles that were breaking off an atom was called the alpha particle. The alpha particle is a very small particle that can break off larger nuclei that are unstable. And really, the alpha particle is about the size of a helium atom. If you remember, helium has a mass number of 4 and atomic number of 2. In other words, there are 4 particles in a helium nucleus. 2 of them are protons, 2 of them are neutrons. So the alpha particle is really 4 particles that break off the nucleus at a time. 2 protons, 2 neutrons. The symbol for the alpha particle is often the Greek letter alpha, but sometimes He is just used since it's the size of a helium nucleus. Rutherford started shooting helium nuclei at thin sheets of gold foil. Why did they pick gold to do this? Because gold is an extremely malleable metal and it can be pounded incredibly thin. And what Rutherford wanted to do was see what the alpha particles would do. So we shot this positive particle. It was a 2+ particle because it had 2 protons. Originally, he thought if Thompson's model was correct, if the atom was a solid sphere that had electrons embedded in it, these alpha particles would not be able to get through. And he was shocked or surprised to find out that the alpha particles, by and large, a ridiculous large majority of those alpha particles went right through the gold foil. So right here is the radioactive source. I thought he used radon. I can't remember for sure, a radioactive element that allows helium nuclei to break off. So these helium nuclei would come shooting out. They'd put the radioactive stuff inside a box with a little slit. And alpha particles would break off and go flying right through. And he saw that most of them went right through the gold foil. How did he know most of them went right through? Because he surrounded the gold foil with fluorescent paper. And when those alpha particles were traveling, they had a lot of energy, and the fluorescent paper would light up right on the other side of the gold foil. Occasionally, the paper would light up on the sides, though. In other words, the alpha particles weren't able to get through the gold foil, and instead, well, they got through the gold foil, but they were deflected. Well, the fact that most of them went right through, Rutherford realized there was a problem with Thompson's model. Rather than the atom being a solid sphere with electrons embedded in it, if the alpha particles got through it, that would mean that the atoms had to be mostly empty space, since most of the alpha particles went straight through. Since some of these positive alpha particles deflected to one side or the other, Rutherford realized that there had to be a positive area inside the nucleus, or inside the atom, which he called a nucleus, which deflected or scattered the alpha particle. Every now and then, one of the alpha particles came flying right back, which meant that inside the atom there had to be a tiny, tiny, highly dense area which would cause that alpha particle to smash and bounce right back. In other words, all the mass in the atom had to be concentrated in an extremely small space. So he knew that inside the atom, all the mass had to be in a small space, and that mass had to be where the positive charge was in order to deflect the particle. So a new model arose. It was called Rutherford's nuclear model. It was the first model that introduced the nucleus, and he had electrons orbiting the nucleus instead of actually inside the atom. Sometimes the atom's called a planetary model because Bohr's model comes out right after this. And we'll talk about why it was called the planetary model later. And a big problem arose. If the electrons were negative and the nucleus was positive, what kept the electrons in orbit? And the protons alone didn't account for the mass of the atom.